In today's world, health risks posed by a polluted atmosphere have significantly escalated along with urbanization. The problem of air quality monitoring is increasingly challenging due to the high accuracy required for air pollution prediction in short horizons or nowcasting, particularly in extreme events under the impact of climate change. Scientists at the University of Technology, Sydney and New South Wales Department of Climate Change, Energy, the Environment and Water have collaborated in the development of learning models for air pollution forecast in Sydney and the creation of a user-friendly visualization dashboard. The platform, providing spatio-temporal observations and predictive air pollutant data, integrates information from the models with meteorology monitoring stations to improve the accuracy and reliability of the forecasts. Dependable systems have been developed for data fusion of the sensors with all other sources and for blending the models. Dependability in the context of monitoring refers to a system's ability to provide reliable, accurate, resilient, and timely data, even when faced with uncertain or challenging conditions. In our proposed dependable monitoring system, it integrates the redundancy in hardware and decision-making processes to ensure the quality of data at any time. In this translational research, we developed a dependable configuration for low-cost air quality sensors through both hardware and software layers. First, hardware redundancy is implemented by deploying multiple sensors, collocated at each monitoring site to obtain the most reliable readings from the on-duty sensor of sensor motes in the face of any failure or imperfectness. Next, dependability is reinforced through a decision-making algorithm built from the Dempster-Shafer evidence theory. This theory effectively handles uncertain and conflicting evidence for validating sensor readings against reference grade stations. By combining evidence from multiple sensing sources, this mechanism can ensure consistently accurate and reliable data. With quality-enhanced sensor data obtained from the dependable monitoring system and prediction models based on deep learning, we were able to train an Ensemble learning model for nowcasting. This model is built from deep neural networks, leveraging the strengths of individual models in capturing distinct patterns from the input data to adapt to varying temporal dynamics. To increase reliability, we also created another model trained on monitoring station data. The final Ensemble model aims to accurately predict air quality conditions for the next 3, 6, and 12 hours. Finally, the forecasting results are transferred to the department's central database, where they are retrieved and processed by the logic in the back end, and then displayed on the user-friendly interface of our developed visualization dashboard. Here is our dashboard in its forecasting mode, where users can visually access air quality information by exploring the lists of available options in the left panel. For example, let's look at the distribution of fine dust PM2.5. The 3-hour prediction at Lidcombe suburb with our Ensemble learning and purple air sensor data can be viewed online. By clicking on the sensor marker, the sidebar appears with the time series graph, displaying both historical and nowcasting profiles. The Reset Selection button is used to clear all choices and start fresh to explore different forecast options. Now, let's explore the case of 6-hour nowcast with the same sensor. After all 5 parameters are chosen from the selection panel, the ranking panel on the right immediately replaces real-time monitoring data with the highest pollutant concentration in the selected forecast. Clicking the sensor marker opens its sidebar, and users can easily navigate through the prediction timeline using the time slider above the map to automatically traverse consecutive forecast points in the prediction horizon. Moving to the Sydney Southwest region, we will see the implementation of the Ensemble model's application in nowcasting air pollution using data from a state-run monitoring station. For this example, we'll focus on Liverpool Station. The time series graph shows a slight inclination after the peak PM2.5 in the historical data, followed by a sharp decline predicted over the next 6 hours by the Ensemble model, aligning closely with past trends from observations. The sidebar also shows the performance metrics of the forecast compared to the observed concentration. The forecast horizon can be extended, for example, to a 12-hour period. The graph illustrates a transition from a fair to a good air quality level for PM2.5 at Liverpool. Below the forecast graph, performance metrics are shown to provide scientists with a quick assessment of forecast accuracy, reinforcing research integrity. In addition, the dashboard relays recommended activities by the New South Wales government, allowing users to make informed decisions based on the air quality forecasts they see. Overall, the dashboard could be used to support the authority and general users with informed decisions based on accurate and reliable forecasts of urban air quality in addressing sustainable development.